In this video, we're going to discuss trends in the transition metals of the periodic table. So remember, our transition metals are the D element, this block in the center of the periodic table. The fourth period has the 3Ds, the fifth period has the 4Ds, the sixth period has the 5Ds, and the seventh period has the 6Ds. They're out of sequence by one. Remember that we always fill the next S orbital before we fill the D orbitals in our filling pattern. So they're a little out of order, and this leads to several interesting complications in their behavior. So let's explore those a little bit. First and foremost, the atomic size variances. You notice as we go from potassium to calcium or calcium to gallium, we see a rather large decrease in atomic radius. While we're in the p block, we see a much smaller change. Well, as we're filling the p orbitals, it's the same set of orbitals, so they're all relatively at the same distance. This happens for our d orbitals as well. What we'll find is that there's not a large variance in the size of our d orbital atoms. A little bit early on as we first start to fill them, but quickly it levels off to a pretty consistent size throughout the transition metal series. Similar behavior is seen for the fifth and sixth periods as well. The atomic size does not change significantly across the D series, and its largest change tends to happen at the very beginning. When we take a look at electronegativity, much like the P block, where as you go more to the right, or the S block, as you move more to the right on the periodic table, you become more electronegative. The idea was our Z effective was increasing. We were adding more protons to the nucleus, but we weren't adding more shielding electrons. And as a result, the electrons could get pulled in a little tighter, they could be bound to that nucleus a little stronger, and it became harder to remove them and more favorable to add one. We see a largely similar change through the transition metals. It's not as pronounced as we might see for the S or P block, but as we move to the right, we do see an increase in electronegativity. Additionally, while we can't see it here on these small graphs, we also see an increase as you go down the column. Now, this might seem a little odd. Normally we think of electronegativity, the most electronegative elements are in the upper right of the periodic table. If you were to look at fluorine and chlorine and bromine and iodine, we would expect fluorine to be the most electronegative. Within the transition metals, though, there's a general trend that you're more electronegative as you go down the column. This has to do with atomic radius changes. We'll see in a little bit. But the sixth period and the fifth period are effectively the same atomic radius. But the sixth period has a greater number of protons in the nucleus, and as a result tends to attract electrons a little stronger, tends to hold on to them, and as a result just tends to be a little bit more electronegative. And so while left to right, the transition metals do follow our standard behavior, they tend to have a reverse pattern for electronegativity than we would expect for the rest of the periodic table. And finally, if we take a look at ionization energy, from our S elements or our P elements, we tend to see a fairly large increase as we move from left to right across the periodic table. Within our D block, however, this is a fairly minimal change. There's a little bit at the end here for zinc as we finish filling the entire D block. But as we travel from left to right, the changes are very small compared to what we expect for the S and P blocks. The cause of this, if we think about it for a minute, is remembering that what's your ionized electron? It's your outermost, highest energy electron. Well, that's not going to be the D. In this block, we have 4 S's and 3 Ds. The first electron that is lost when you ionize a transition metal actually comes out of the 4s. As a result, even though we're talking about various other elements with more and more d electrons, the ionization that is occurring is out of the 4s for all of them. This is why we don't see a significant change in ionization energy as we go through the transition metals. We're not significantly changing the nature of the orbital that the ionization is occurring in. For every increase in a proton in the nucleus, we're actually adding an extra electron to the core, causing an extra electron's worth of shielding. So as far as that 4s electron is concerned, one extra positive and one extra negative cancels out and doesn't really change how attracted it is to the nucleus. Z effective for our electron that gets ionized looks the same as we go through the d metals. If we want to explore this for more than just the 3Ds, we can look at these graphs here that talk about atomic radius and our various series. And what we see is that, indeed, as we go from the 3rd series to the 4th series, we see that there is an increase in the radius. This follows the general trend that as you go down the periodic table, your elements should get bigger. A 4D orbital should be a little larger than a 3D orbital. However, as we go from our 4D to our 5D, these radius are almost identical. Why aren't we continuing this trend? Why aren't we continuing to see the expansion of the orbital? Well, at first we do, but remember that every time you add another proton, your orbitals tend to contract. They get a little bit smaller. The 5D have the Lanthanides. If we scroll back up periodic table, our 5D here show up at period 6, where the Lanthanides appear. There's a whole series of f orbitals that add more core electrons that have to occur before we reach the 5Ds. As a result, when we went from the 3Ds to the 4Ds, well, we just had the S and the P in between. This involved some amount of contraction, but the 4D would be a little bit further out. When we go from the 4D to the 5D, we get the S and P and additional contraction due to the Fs, bringing the 5D even further in until it just happens to be about the same size as the 4Ds. So it's a bit coincidental, and they're not perfect. There are slight differences that you can spot in a few places, but in general, they have nearly the same radius. As a result of this, the density of these elements changes extremely. As we go from our 3Ds to our 4Ds, we're a little larger, but we have a lot more nucleons in the nucleus. And so mass over volume, we tend to get a little bit more dense. But since when we go from the 4D to the 5D, the volume doesn't change, just the mass in the nucleus, we see a much larger increase in density. Our most dense elements, like tungsten and iridium, are here at the bottom of the transition metals. Additionally, we see this in our ionization energies. Our 3D elements can ionize and lose their 4s electrons. Our 4Ds can ionize and lose their 5s, and so on. But as the contraction continues, well, our 4D and 5D, as we compare them, we have more positives in the nucleus, we have more contractions of the core electrons. Our outermost electrons in the 5Ds tend to actually be harder to remove than the equivalent electrons in the 4 and 3Ds. Because of the amount of contraction and the increase in the number of protons in the nucleus, for equivalently the same distance, it is harder to remove that electron off of gold than it is off silver or copper. Same with iridium off cobalt and rhodium, or osmium off iron and ruthenium, and so on. As a general trend, the later transition metals are just harder to remove electrons from. Why we don't talk about the 6D elements is that most of them aren't stable. So we get to radioactivity, we'll discuss it, but they tend to be highly unstable elements and not things that we can readily do experiments in chemistry with. But to recap, as we see our transition metals, they tend to be fairly small changes as we go through the D series compared to going through the P or the S series. We don't see a large change in electronegativity from left to right, a little bit. We don't see a large atomic radius change from left to right, just a little bit. We don't see a large ionization energy change left to right. However, vertically, we do see some more pronounced changes. Going down a column, we tend to get more dense. Going down a column, we tend to be more electronegative. And going down the column, we tend to have higher ionization energy.